Hi, hello, how are you? I'm Craig Chapman and welcome to part 3 of my series on experimenting with neural network simulation. Now, I've been giving some thought to how many more parts I want to put in this video series, and it certainly seems to me that training the neural network, the algorithm which is known as backpropagation for training the network, really deserves a video of its own. So that's going to be part 4. So in this part 3, we're going to work on getting to a point that we can process the network forwards with data, and what we'll get will be effectively nonsense results, and we'll only start making sense of those results in the next part. But I decided to make this a part in its own right because there are some missing components to our network still at this point, and I've actually decided to make a small design change. So I'm going to go ahead and open up an Excel sheet and just give you a brief overview of the design change that I plan to make. Okay, so here we are in Excel and we're looking at a model of the neural network we were looking at building in part 2. So we have 4 input neurons, 3 hidden layer neurons, and a single output neuron. Now, one thing that I deliberately omitted from this network was neurons. We have axons, which is originally I was going to call the axons array neurons, but I thought better of it. So I omitted the neurons because my thought was we could put the number of neurons into the layer data structure, and then we could divide the number of synapses between first and last synapse by the number of neurons that we were planning to run through, and in doing so we could figure out which synapses belong to which neuron. Now, that is perfectly acceptable for the actual processing side of things, but it does make the code a little bit more difficult to write, and it actually makes our network a little less flexible. For example, if I wanted to have a neuron with, say, 3 synaptic weights instead of 4, so suppose I want to break one of the links between the input layer and the hidden layer, well, I can't do that with this structure because we're assuming that all of the neurons in a layer have the same number of synapses. Now, it's not very common that you would want to do that, but it is possible that we might want to do that in a simulation in the future. It also, as I said, just makes the code a little more difficult because if we had a structure representing the neurons, then each neuron would tell us its first and last synapse, and the layers would tell us which neurons we should be looking at. So I've mocked up a model of this. So in the layers here we have 0 to 3. Well, these are neurons 0 to 3. There are 4 input neurons. And you can see I've changed the name here from synapse to neuron, so first neuron to last neuron. And then the neuron itself would have a first synapse, a last synapse, and an index to the axon for this neuron. So that's where we're going to put our result. So our algorithm, when we come to run the network forward, will be able to look at the neurons array and say, well, I'm going to work on neurons 0 through 3 based on the layer, and split those up into separate threaded tasks. So I've decided that I'm going to go ahead and alter our code to support this neurons array, and at some point in the future, possibly not for this video series, I'll modify the code a little bit more on that base class so that we can have a flexible number of synapses to each neuron, a flexible number of neurons to each layer as we already have, and so on. So that's what I'm going to do with the first part of this video, and then we'll look at writing the code to process the network forwards and get a result. So let's go ahead and get started. Okay, so here I am in our neural net custom code, and I've gone ahead and made the changes, so I'm just going to step through and show the changes to you, show you what I've done here. The first thing I did is I altered our T-layer record. So it used to have the first and last synapses of the layer, but now it has the first and last neuron and the bias value. Now you'll remember that we spoke about the bias in a previous video. Well, most neural network implementations have a single bias for an entire layer of neurons, and so that's why I've put the bias value here, and we'll come back to that and look at that later. I've also added the T-neuron record type. Now this is going to give me the first and last synapses of the neuron and the target axon. So that's the axon that we're targeting to put our result into. So then what I had to do, of course, is add a neurons array into our class. So I've added here simply fneurons array of T neuron. And then we need to initialize it. So I've set the length to the total number of neurons, which you'll remember we got the calculation total neurons plus input neurons for the axon array. So I have the same array here, or the same value here I should say, but for the neurons, and we only need the neurons. We don't need input neurons because the input neurons are actually kind of dummy values in the axon array. Then, after initializing our layers, I initialize the neurons. Now the initialize layers function has a change, and I'll show you that in a moment, but initialize neurons basically sets the first synapse, last synapse, and target axon value for each of the neurons in each layer as we go through. And then in the destructor here, I don't forget to clean up my neurons array. So now let's go take a look at the initialize layers function. Well, this is the old function, and what you can see here is in the input layer we went from first to last synapse. Well, of course we're not doing that because now our layers are first to last neuron. So I'll delete that out, and I have the replacement right here. So what we're doing is we're looping through from 0 to pred of L, which is the length of our neurons per layer. So this is going through the layers. For each of the layers I'm initializing the bias to 0. The first neuron to NIDX, which is initialized to 0 here. Then I'll add the number of neurons per layer, less 1, to the NIDX value, and that gives me the last neuron for this layer. And then I increment NIDX because if the last neuron in this layer is neuron 3, for example, on the input layer, then the first neuron in the next layer is going to be number 4. So that's how we calculate the neurons in each layer. And then I've got this new function, initialize neurons. Well, this is broken into two parts. So the first part being the input layer. Well, the first synapse in the input layer is going to be the neuron index. So I'm looping through 0 to the number of neurons in the input layer, so layer 0. And the first synapse is going to be the same as the number of the neuron, as is the last synapse, because each of the synapses in the input layer has a single, each of the neurons in the input layer has a single synapse. We also have the axon index. Again, for the input layer, that's just going to match the number of the neuron. So the axon in the axon array, axon 0 is going to be for neuron 0 to target, and so on. Doing our little trap here to make sure that if we only have one layer we exit out. And then I get the N offset. Now this is the neuron offset. And what I'm doing here is I'm saying get the number of neurons in the input layer. So if the input layer has, as in our case, 4 neurons, then we know that we need to start at neuron number 4 and start adding from there. So that's my neuron offset, and you'll see me use that in just a moment. And then I have SIDX, which is synapse index. Now because each of the input neurons has a single synapse, then it matches N offset. It's going to have a single synapse per neuron in the first layer. So now I'm going to use L index to loop through the remaining layers. So that's 1 to pred of L. And then I'm going to use my N index to loop through the neurons in each layer. So from 0 to the number of neurons in whichever layer we're looking at, LIDX. So the first neuron, I'm going to add NIDX, so this is the first neuron in this layer, which is numbered 0. So I'm adding the N offset, which again, based on our example numbers, is number 4. So 4 plus 0 is 4, and that's the neuron that we want to address. We're going to set its axon to the same value. And then if we take a look at the synapse, well, I'm addressing the neuron in the same way, but the first synapse I'm using the SIDX, the synapse index, and then I'm incrementing the synapse index by the number of neurons in the previous layer less 1. So that's going to increment our synapse index to give us the last synapse, and then we increment the last synapse because the first synapse in the next layer of neurons, or the first synapse for the next neuron, is going to be this last synapse plus 1. And then of course I'm incrementing the neuron offset at the end of processing each layer so that we step onto the next layer's neurons. So I hope that much is relatively clear. Let's step up to this last little function here. Initializing the synapses has to happen a little differently. Now the way we were initializing the synapses before is we were going from first synapse to last synapse on a layer, but those variables don't exist on a layer anymore, so we have a replacement, For the input layer, we're going from synapse 0 to whatever number of neurons is in that layer, because again on the input layer we have one synapse per neuron. And so the rest of the code remains the same, using the same indexing. And then once we get through to the remaining layers, I have here where we have layers first synapse to last synapse. I'm doing almost the same again. What I'm doing here is I'm saying look into the neurons array for the first neuron and get its first synapse, and look into the neurons array for the last neuron and get its last synapse. So the loop works in exactly the same way as it did at the end of the previous part of the video. We're just getting the data from a different location now. And for the remainder of that function, it works in exactly the same way. So what I've done, having made these changes, is I've reintroduced the dump function. So if I come down here, I've added a dump function for axon, synapses, neurons, and layers. And I'm going to leave this in for a little while just so that we can keep this ability to debug, but I'll remove it when we no longer need it. And I've gone ahead and run the numbers, and these are the results. So you'll remember that axons 8, 9, 10, and 11 are our input axons, and they used to have a value of 200. I didn't reintroduce that, so I'm going to get those 4 out of the way. So those 4 input axon values are being picked up by synapses 0, 1, 2, and 3. So if we take a look at those, you can see they're picking up 8, 9, 10, and 11. So that's all working correctly. Then our hidden layer neurons, well, let's see, 1, 2, 3, 4 for the first hidden layer neuron, 4 for the second, and 4 for the third hidden neuron. So we're indexing again 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So we're accessing the axons of neurons 0 through 3 up here with those synapses. Okay, so we'll get rid of those values. And then we have our output layer, which is a single neuron which has 3 synapses, and the synapses pick up values from 4, 5, and 6. Those are our hidden layer, and the output value is going to go into 7. So we don't need to worry about those synapses. Those are looking correct. Now the output value is going into, as I said, axon 7 here. So let's look at our neurons as they come out. Well, the first synapse on the input layer, neuron 0, is going to be synapse 0, and it's also last synapse 0. And this is true for the first 4 because they're the inputs. So 0, 1, 2, 3, and 0, 1, 2, 3. And the target axons are 0, 1, 2, and 3. So that's our input layer targeting 0, 1, 2, and 3. Then the 3 hidden layer neurons, where we have synapses 4 through 7, 8 through 11, 12 through 15, they're all correct. And they're targeting 4, 5, and 6. So we know that that's working correctly. And then the final neuron, which is in the output layer, well, the first synapse is 16 through to synapse 18, so that's picking up the values from the previous layer, and the target axon is 7. So that's all working as expected, and so our network is ready to run. Now before we do run it, there is one more thing that I want to make a change on here. If I come back into our code and take a look at where we initialize our synapses, the input layer, I've actually changed the weight to 0. You'll remember that I was doing a random weight. Well, I'm changing the weight to 0 for the input layer. Why am I doing this? Well, because the input layer doesn't actually need weights. The values are going to be transferred from the input axons directly into the input neuron, and that's going to be its axon value. So we don't need to do any processing in terms of the input neurons with regards to their input values, because they're not connected to neurons in a previous layer. It is the input layer. So I've set that weight to 0, and that will remain at 0. Our processing will not be touching that. Okay, so at this point we're going to begin writing the code to process our network forwards to get a result. And the result is going to be effectively garbage. Until the network is trained, the results that come out aren't really going to be particularly meaningful. So I wanted a way of testing that our network was doing what it should without having to train it first. And the only way to do that really is to put in some numbers and do the math independently of the program and check the results. Well, fortunately, this article written by Matt Mazur, I hope I pronounced that correctly, is on how the backpropagation algorithm works. It works in it's the exact same technique as we're going to be using for both forward and backwards processing of the network. So if you want to see what's coming in video 4, go ahead and take a look at this article, URL right here, because this is effectively the same thing. But what's really useful and convenient about this article is Matt first processes the network forwards using actual values and numbers plugged in, and he does all of the calculations for us and gives us the results. So if we clone this network topology, so we'll have 2 input neurons, 2 hidden layer neurons, 2 output neurons, and the same synapses in between. By cloning this, we can actually make our network calculate the exact same, or perform the exact same calculation, and we can confirm our results against Matt's article, which is very convenient. Thank you for writing this article, Matt. It saved me doing the calculations myself. So what I've done is I've built an Excel sheet which actually runs through these numbers. So here we have 2 input layer neurons. We have 2 input values, so 0.05 and 0.1. We have 2 hidden layer neurons, and here are the weights W1 through W4, which are effectively the synaptic weights 1 and 2 connecting to inputs 1 and 2, 3 and 4 connecting again to inputs 1 and 2, but for the second hidden layer neuron. And then we have W5 through 8, which connect into the hidden layer. And Matt also gives us a couple of convenient bias values. And again, following the equations, he's using the same technique as I'm using for my network here. So following these equations, we have these results, which I have confirmed against Matt's results. So if we run our neural network processing forwards and we get these same 2 output values, then we know that our neural network is doing what it should, even though we don't actually have a sensible result yet. I've only simulated as far as forward processing. We'll look at the backpropagation, as I said, in the next part, but let's go ahead and start writing our code to process our network. Okay, so here I am looking at our iNeural Net interface, and we're going to add our first method to this interface. The method will be query. So we're going to be querying this neural net, and we're going to query it using input values, which are an array of t axon value. So we want to pass in axon values for the inputs, and we want to get as an output values array of t axon value. So that's going to be querying our network, and as you can see, we have the t axon value type is not known. So what I'm going to do is I'm going to create a new unit, and we'll call this ai.neuralnet.types, and we're going to move into here the types that we need from our custom implementation. So the first type that we need is going to be the t axon value. I'm going to take that type and move it into our new unit. Okay, and then we're also going to need the net index, or are we? I'm going to leave that as is for the moment, and we'll use us. Actually, I should save the unit first, so let's save this off. File, save as, and this is in the interface section of our source code, ai.neuralnet.types.pas, and so we can now use that into 2 places. And the second place that we want to use this is in our custom unit right here, so that we have access to it for our implementation. Okay, so now I'm back with a working battery in my microphone. I'm sorry for the break there. We are in ai.neuralnet.custom. We have access to our types, and if I go and take a look in ai.neuralnet, we should now have access to the t axon value. Okay, so now we need to start implementing this method. And our class is the tPerceptron class. And I'm going to put in a private section here to implement the methods of iNeuralNet. And this is our query. Okay, so the first thing we need to do to query the network is copy the input values into the network. And that means finding the axons. I appear to not have t axon value here. Let's just check that. Yeah, we need to include ai.neuralnet.types in here as well. And now I see another potential problem. So let's go ahead and save all and do a build. And okay, that's working. If I do a set length on output values of 0 and then build again, yeah, it's as I thought. I got an error here because the data types are being created dynamically by the compiler. Okay, so over in our AI neural net.types, we also want t axon value array is an array of t axon value. So I'm going to take the t axon value array, and in my neural net implementation for both the input and the output values here, I'm going to set that array type, and then in my implementation I'll need the same, and let's see if that compiles. And that compiles. Okay, yes. So because we were passing array of as a parameter, effectively what the compiler does internally is to create an alias type like t axon value array, and it'll create that type each time it comes across the same parameter type. So effectively our neural net input function had a different type to the type that we're working with within the function, and therefore the compiler was throwing an error. Just a little quirk of the compiler there. So now that we're compiling again, we now need access to our input variables, our input axons, and they are in our AI neural net custom class. So if we take a look here, we've got private section with total neurons, total input neurons, and another private section with the arrays. Probably the easiest, not necessarily the best way to solve this problem, is to make these sections protected. Now, this isn't the best way to do this. The best way to do this would be to provide methods on the base class which are protected that provide access to these variables. But in the interest of saving a little time, this is what I'm going to do right now. You don't necessarily have to follow me, and I can always come back and refactor this a little later on. So from our perceptron now, we have access to those variables from the base class. And the first thing we want to do is make sure that the number of input values that we're trying to put in match the number of input values in our network. So if I type self.ftotal input or f input neurons, that tells me that input neurons is the number that we have available. And so I'm going to say if length of input values is not the same as input neurons, then begin, we're going to exit. And we're just exiting with output values set to a length of 0, so there are going to be no results. Now, for the output values, assuming the input values are correct, we're going to set length on output values to the length, or to the, let's see, self.f output neurons. That's what we want. So we're going to set it to the length of the output neurons. So this is just setting up sizes of parameters, making sure that everything is as it should be. Now we're going to copy input values into our network. And the way we're going to do that is a simple for loop for idx 0 to pred of f input neurons. Do begin. And we're going to copy from input values idx, but we need to put them into the input axons. So we have access to f axons, and we're going to have f total neurons plus idx. So that's going to be the input axon that we want to copy our value into, and we pass in our input values idx. Okay, now that we have our input values, we're going to do the processing here, and then we're going to copy our output values out. So let's do that first. Copy output values, And that's going to be another for loop for IDX is 0 to F output neurons do begin. And I need to know where our output neurons begin. Well, the output neurons begin at the end of the axon array less, or the output axons I should say, at the end of the axons array less the number of input axons or input neurons. So our, let's see if I can get this right, F axons, let's do length F axons, so that gives me the number of axons, L less F input neurons, that should give me the first output neuron. So we'll take that as our value, plus IDX, and that's going to be F axons. Okay, so that should be our output value, and we can simply set output values IDX to F axons and get the values from the axons array. Now if I've got that wrong, when we run it we will get an index out of bounds type error, and I'll know that I got something wrong there. So let's go ahead and get started with the processing here. Now I think that in the interest of simplicity, I'm going to start by processing this all in a single threaded fashion, and then I'll bring in the Delphi parallel programming library to make this multiple tasks. So we'll start with layers. Let's say layer IDX, and this is a tnet index. Now I need access to the tnet index type, and actually this IDX should be a tnet index too. So that means that in our types library we do need to put the tnet index. I'm going to take that from our custom class now. And we'll put that into types. So that's going to give us access to that data type in our perceptron. Okay, so we're going to say for layer IDX is equal to 0, 2, and did I create a variable for layer count? Yes. So we'll do pred f layer count. Do begin. So pressing the wrong key here. Okay. So we're going to cycle through the layers. Now in each layer we're going to get a number of neurons. So let's do for neuron IDX is equal to 0 to, actually it's not equal to 0, is equal to F layers layer IDX dot first neuron to F layers layer IDX dot last neuron do begin. Okay, good. So now we need a neuron IDX up here. And we're going to need a synapse IDX. tnet index. Because we're now going to loop through the synapses of each of the neurons. For synapse IDX equals F neurons neuron IDX dot first synapse to F neurons neuron IDX dot last synapse to begin. Okay, so what we want to do with these synapses is total them up, and we're doing this on a per neuron basis. So let's do synapse sum, and we'll put that to 0. Now synapse sum is a t axon value, and we currently have it set to 0. So what we're going to do is synapse sum plus, and then we're going to add the f neuron idx dot first synapse, or no, we should be doing this on the synapses. Okay, let's get this right. We're going to do f synapses synapse idx dot weight multiplied by f axons f synapses synapse idx dot axon index, so that will give me the axon value. So by the end of this loop, what we have is a sum of each of the weights on the synapses for this neuron multiplied by the axon value that that synapse is connected to. Okay, good. So then we now need to do a little bit of math on this, and that is our sigmoid function that we talked about in the previous part. So as you can see in this expression that I have here, I have 0 minus, and then I've put in the, let's get this right, so I've put in the weight 1, weight 2 multiplied by their respective input values, and I've then added D9, which is our bias, so I'll add that to our result in a moment. We're subtracting all of that from 0, and then we're doing an exponent on it. So let's do that bit first. So the first thing we want to do is synapse sum plus, and we want the bias on this layer. So we'll say f layers layer idx dot bias. Okay, so that's done that part of this expression. Then we're going to do synapse sum is equal to 0 less synapse sum. So that gets us the next little part of the expression there. We're then going to exponent on the whole thing. Synapse sum is the exponent. Synapse sum. What's next? Our next step is to do 1 plus the exponent and divide 1 by the whole thing. So synapse sum becomes equal to 1 divided by 1 plus synapse sum. Okay, so that gives us our total value in this synapse sum variable here. And then finally, for processing this one neuron, we need to put that into the appropriate target axon. So we're going to go for f axons, and we're going to say f neurons neuron idx dot axon. Why am I not getting that? Input values, output values. F neurons neuron index dot. I'm sure it's supposed to be axon here. Yes, that's the target axon, equal to synapse sum. Let's see if that builds, because it seems to have a problem with that, but it might be that typo. Okay. There are warnings, but it compiles. Okay, so we're now running through processing all of that data, and we have our output. Excellent. Let's see if this works. In order to see if it works, we need to build a test program. So I'm going to add a new project. Let's just do a console application, I guess, for the moment. And I'm going to go ahead and save all of this off. So under samples, what I'm going to do is forward only. I'm just going to put forward only for the project name, and we'll put forward only. Okay, do I want to save the project group? Sure. Okay, and I need to give my project access to my AI units. So I'm going to set all targets, show path, and from where I am, it's going to be up 1, 2, source API. Select that folder, so it's going to be up 1, 2, source API. Add that in. interfaces, and why not implementation for now. Okay, so we have the directories in. Now what I should be able to do is use this ai.neuralnet and ai.neuralnet.perceptron.cpu. I'm actually going to create an API unit later to make this a little more convenient, but for right now. And then we'll have a var. Net is iNeuralNet. And then in here we'll do net equals tperceptron.create. Now I need to give that the neurons per layer, and we'll go take a look at that in a moment. We need to make sure we do net nil at the end. So let's try and finally put the net nil in the middle there. I probably don't need to do that with automatic reference counting, but I feel more comfortable doing it. And then in here we're going to do net.query, and we're going to put some values in and out of there. Okay, so before we get writing the inputs and outputs, it happened quicker than you saw it, but I took a break from recording and noticed a problem in the AI library, and so I've annotated the video. Let's go take a look at that problem. It was with this copying of the output values and how I calculate the location of the output axons. Clearly being a little bit stupid or tired, because the output axons should be quite easy to find. What we do is we take a look at our layers. So we already know how many layers there are. Let's go f layers, and then it's self.f total layers, or f layer count. Okay, so that's going to give us our layer count. We do pred of that, and that gives us our last layer. And our last layer has a first neuron and a last neuron. Well, the first neuron is actually where our axons begin. So we're going to take that, and our output values will actually be, let's see here, the first neuron plus the IDX value. And that's how our output layer should work. So hopefully that is going to prevent us having an error in a moment when we run this network. Now, the network that we're simulating is this one. It has 2 input layer, 2 hidden layer, and 2 output layer neurons. So this is 222. If we come back into our test program source, forward only, this is going to be a network of 222. And then we're going to query it with the same input values. So let's go and take a look. Whoops. Let's go and take a look at the input values. And we have 0.05 and 0.1. So let's put those values in. 0.05 and 0.1. So that's our input values. Now our output values we're going to put into an output array. Output values. And this is going to be T axon array. So that's a data type that we need to gain access to. ai.neuralnet.types. Okay. And we're going to pass in, did I get that wrong? T-axon value array, I did get that wrong. So let's go and change that type. Okay, and that's going to be our output values. Now we want to write our output values to the screen. So I'm going to do some writeline here. We're going to say if length of output values is 0, begin writeline, oh no, something went wrong. So that's because if we get the wrong number of inputs or outputs, then we're catching that error. And then we're going to do a for IDX, which is going to be IDX T net index. We're going to go from 0 to the length of the output values. We're doing a pred. Do begin writeline, and we'll put, let's see, I'm going to put a tab, or 4 spaces, plus float to string, output values IDX, and you know what, why not put an index on this? So we'll put int to str IDX plus, and then we'll add in a colon just to make that look pretty. And then before we exit the program, we'll do a readlin, so that'll keep the program open. Now when I run this, assuming it builds and runs, I'm not expecting to get the same values as in our spreadsheet yet. And the reason for that is these weights are pre-programmed for testing. So I'm going to go in a moment and hard code these values in so that we can test our network. The same is true of the bias values. So in a moment I'll go and do that, but first let's just see if our program runs. And we do indeed get some values coming out. Great. So now let's go and pre-program in the values to make this function the way that it should in our perceptron. Hard coding some values here because it's good for testing. Okay, so the first thing that we want to do is program in the synaptic weights. Now remember that our input synapses, so the first two synapses in this case, are 0. They are simply there to, should they be 0? They should be 1s, because when we multiply the input values by 0, we'll get 0. So let's go and take a look again at our custom here. And we want to take a look at where we initialize synapses, and synaptic weights of the input layer should be 1. Okay, let's make sure we get that right first. So we need to skip the first two synapses, and then we're going to program in the synapses from here manually. Let's see what's the easiest way of doing this. I guess I'm going to split my screen in two for a moment. And we're going to just do this hard coding by hand. So we'll go F synapses, and we're starting at not 0, not 1, but 2. Dot weight is going to be 0.15. And I won't make you watch while I do all of these, so I'll just speed up the recording here. Okay, so I've hard-coded in the 9 weights, or 7 weights. I think have I got that right? 1, 5, 2, 2, 5, 3, 4, 4, 5, 5, 5, 5. Yes, I got that right. And then I've put in the two bias values, 0.35 and 0.6. So I've manually coded those in. Let's go ahead and see what happens when we run the program now. Okay, so we're getting a couple of values coming out here, and they look correct to me. Let's go ahead and check them against our spreadsheet. So the first output is 0.75. So yeah, it's a little off, and I'm guessing that that's going to be a rounding issue. Okay. So now I guess it's time to do a little debugging on this. So I'm going to go ahead and debug this, and I'll come back to you when I discover exactly what the problem is. Okay, so I did a little debugging, and here's what I found. The first problem I found is that our input layer was going through this math, which it should not be. The input layer should simply be the sum of the axon that it's retrieving from the input array multiplied by the weight, which we set hard-coded to 1. So it shouldn't go through our expression here because it's not really a neuron, it's just an input value. And so what I did is I said if the layer IDX is greater than 0, then we'll do the math. But if we're in the input layer, we'll simply store the axon value as a return. The second problem I found was actually a rounding issue. So in our forward-only example here, I just stuck a bunch of zeros on the end of the input values, and with those two changes, let's go ahead and run the program up, bring it over the side here, and pull up our spreadsheet. You can see here that 0, or rather the first output layer, neuron reads 0.751365, 0.751365, and then we start to get a little off with the rounding again. So I've got 0.7, and here we see 0.65 and so on. That's just a rounding issue which we can take care of a little later. And the second output neuron, 28476, whereas here we've got 465. So again, just a slight rounding error on the input values, but generally it's working approximately correctly. So I'm going to do a little bit more debugging on the rounding issues and see if I can resolve some of that, but at the moment I think this is close enough to within 4 or 6 decimal places, so we're getting pretty close. Now, unfortunately, recording time for me is running very short today, and so I'm not going to have time to do everything I wanted to do, which is to fix the rounding error for one and multi-thread the processing code. So what I'm going to do, I know that I said the next part would be part 4. Well, it will, but that will come after part 3.5. So I'm going to put another video together at some point next week, part 3.5, where we'll take care of multi-threading our processing, and then we'll get part 4 where we look at the training part. So until next time, thanks for watching. My name's Craig Chapman.